Welcome back everyone. This video will cover tungstens and filler rods. On page 33, tungsten electrodes have the highest melting point of all metals, and they keep their hardness even when they're red hot. The tensile strength is upwards of 500,000 psi. Comparing that to mild steel's tensile strength is 50,000 psi. It's quite a big difference. Elements are added to pure tungsten to elevate the melting temperature, making it even stronger. Three main electrodes are pure, thoriated, and a zirconiated tungsten. Pure tungstens are abbreviated with EWP, E standing for electrode, W stands for tungsten, and P is for pure. These are used for welding alternating current high frequency on aluminum and magnesium alloys. They have a green band and it is preferred to ball or round the end for welding. Here we got thoriated tungstens. They are ran on direct current electrode negative with a pointed end. The pointed end can also be referred to as conical. Just another term for pointed end. Thorium increases current carrying capacity and improves starting the arc. A yellow band has 1% thorium, and a red band, which is more common, has 2% thorium added. One thing to really know about this stuff is that when it's ground, when you're grinding it to a point, the thorium in this material can be radioactive, so make sure to mask up. A zirconiated tungsten is used for high quality work on aluminum and magnesium. It is recognized by a brown band, produces a stable arc, and is highly resistant to corrosion. These are ran on alternating current high frequency with a rounded end. Two standard electrode finishes are standard and ground. Ground is for more precise work. The current depends on the base metal thickness. We covered this earlier, but direct current electrode negative has the greatest carrying current capacity. It does not break down the electrode. AC has a bit less, it's distributed half and half. And electrode positive has the least because it just consumes the electrode, there's too much heat. Page 37. Balling a tungsten is done by running direct current electrode positive briefly. This should be done, the ball should be no larger than 1.5 times the electrode diameter. This preparation is used for welding alternating current high frequency on aluminum. If you touch your tungsten to the work, it is most likely contaminated, so make sure to break off contamination with pliers and reball it to keep a clean weld going. If you get a dirty tungsten, welding becomes slower and much harder. And most of the time, you don't have to spend a bunch of time balling your tungstens. It does make nicer weld, but most of the time, the electrode will just ball for you when you're welding. A conical end is used with direct current electrode negative on mild steel and stainless. Tapering can be done by grinding, which is most common, or by dipping in a chemical solution, which I wouldn't recommend. But they do have it out there. You can taper a tungsten with a torch and a pinch, but it does make the electrode brittle. The taper should be 2 to 2.5 times electrode diameter, and always knock off the fine point so it doesn't show up on an x-ray. And for you guys out there, you're going to find what you guys want to do and what works best for you for your pointed electrodes. But this is rule of thumb for testing information. Prevent contamination. With practice, it is less likely to touch the tungsten to the work. Touching your tungsten to the work does create a ball like you see over here. It contaminates the electrode. This has to usually be ground or cut off and then repointed. Post flow is very important for protecting a cooling weld. And post flow is also important for keeping the tungsten healthy. For every 10 amps, there should be 1 second of post flow time. So an example you see on the screen, for 110 amps, you would have 11 seconds sitting there for post flow, or post flow coming out of the torch. And for a bald tungsten, just have good pliers with you to break off the contaminated part of the tungsten. As a summary, one thing in case I missed it, if the electrode is too large for the current, the arc will wander. Third section in your book, welding on mild steel. Page 3, filler rods are 36 inches in length and are copper coated to prevent them from rusting. They are explained like most filler materials. ER70S2 is an example of a commonly used filler rod. E stands for electrode. R stands for rod. 70 is the tensile strength, and that's of course AWS, American Welding Society, in pounds per square inch. It would be 480 or 48 for the CSA. S indicates it's a solid wire. 2 is chemical composition, silicon, manganese, and they have 3 other oxidizers, deoxidizers in there as well. Page 5, filler rods are deoxidized to help with porosity. Deoxidized mean, if you guys remember from your first metallurgy book and foundations, steel can be rimmed or semi-killed or fully killed. This refers to the amount of oxygen that has been removed from the material. Rimmed, there's no actions taken to remove oxygen. Semi-killed, they kind of care, they removed a bit of oxygen. And fully killed is high quality stuff, they've removed all the oxygen from the material. The filler rods should be stored at room temperature in a dust dry free place. These are deoxidized to reduce porosity. Gas tungsten arc welding creates a puddle fast, which does not allow gases to bubble off, and that creates porosity as well. So that's where these filler rods help to reduce porosity in mild steel. Page 5, welding on mild steel. A 2% thoriated on reverse polarity is used. Mill scale must be removed. The cleaner the better. Arc length is generally 1.5 times electrode diameter. Page 6 and 7 show some weld defects. Incomplete penetration. Welding current is too low. Excessive penetration, you have too much current going on. Undercut can be from current too high, moving your torch around too much, or your shielding gas flow too high. Porosity is from lack of shielding, and if you see any dark spots around a weld, that's also from lack of shielding gas. Burning through is from going too slow or having too much current. Suck back is pretty common. That's usually from the root bead. The root bead draws back into the joint. This is a problem with overhead because of gravity. If you spend too much time in the middle of the weld and you're not putting enough filler metal in the weld, it's going to take material from the root pass and suck it towards the torch. And then you're going to have a concave inside of a joint, which is a defect. And tungsten inclusions, that's from your electrode touching the workpiece. This leads to porosity and cracking. A tungsten inclusion will always show up on an x-ray, so if you ever touch your tungsten to work, it's good practice just to stop and grind that part out. Go resharpen your tungsten and start again. But we'll practice all this in the shop, of course. Here's a summary for this section. There will be one more video after this to finish the book.